Okay, well, maybe we'll get started now. Just a bit about procedures. So if you have questions during the talk, please type them in the Q&A box, and I'll either read them out or unmute you if it's a complicated question. And at the end of the seminar, you can either type questions in the Q&A or raise your hand to be recognized. So today it's a great pleasure to welcome Professor Hiroko Watanabe of Tohoku University in the Research Center for Neutrino Science. Dr. Watanabe started her research on neutrinos with the KamLAND experiment already as an undergrad at Tokyo University of Science, where she got her BS in physics in 2007. And then she moved to Tohoku University, where she took on a major role in many aspects of the anti-neutrino analysis of the KamLAND experiment. The motions of the Earth's crust and mantle caused a brief delay in the thesis writing due to the Great Tohoku earthquake of 2011 and magnitude 9.1 and the subsequent tsunami, which led to a month of difficulties getting heat, water, electricity, and other such luxuries. She completed her PhD thesis the following year in 2012, and she received many prizes and so impressed the faculty that she was immediately appointed as a professor there and stayed in Tohoku University ever since. And we should congratulate her on getting tenure last year. Next month, she'll receive the Fumiko Yonezawa Prize of the Physical Society of Japan for her work, and she's a member of both the Physics Society of Japan and the Geoscience Union of Japan. So in addition to the work on geoneutrinos that are her topic today, she's worked on neutrino astrophysics, like beryllium-7 and boron-8 solar neutrino measurements, limits on neutrinos from pre-supernova stars and such like, and on pure physics, such as neutrino oscillation parameters using solar and reactor anti-neutrinos, double beta decay. She's made major contributions to the first detection of geoneutrinos from uranium and thorium decays that heat the Earth's interior. She's worked on modeling the 3D composition of the crust in Japan and subsequent predictions for the geoneutrinos, but she's also worked on the development of liquid scintillators, lithium-6 loaded detectors for directional measurement of electron antineutrinos, and prospects which might in the future perhaps lead to being able to measure, in addition to uranium and thorium, also the potassium-40 decay neutrinos. So the field of geoneutrinos has a very exciting feature of their large new anti-neutrino detectors in Canada and China joining KamLAND last year and next year. So there will be more than one place where these things are being measured now. And I'm sure she'll tell you a bit about the exciting project that she's leading for an even more powerful experiment, the mobile ocean bottom neutrino detector to study neutrinos from the Earth's mantle far away from the pesky continental crust and reactors. So without further ado, Professor Watanabe, Neutrino Geoscience.
Okay, so thank you very much for the introduction and inviting me this very nice opportunity. So as mentioned, today I'd like to talk about the Neutrino Geoscience, which is measuring the Earth's neutrino flux and constraining its composition. Okay, so this is today's content. So let me start from the introduction. So I'd like to start from what is the Earth? So it's very familiar with us, but here is the structure of the Earth. They have the several layers like this. From top of the bottom, it has the crust and mantle and the core, and outer core and inner core. And inner core is almost same scale as the moon. So mass is the 6 times the 10 to 24 kilograms, and the mean density here, mean radius, 6,000. And so I wanted to mention about the elements construct the Earth. So like I listed up here, is the FeOMgSi. It's actually in total the 94%. It comes from these elements, and plus these 3 elements, that's the total is 99%. It's almost made by the elements. Okay, so next is the Earth's structure. So as I mentioned before, it's categorized as the crust, mantle, and outer core and the inner core. So the figure also show the ratio of the each component in terms of the volume and the mass. And the important things is the heat producing element that which is related to the geoneutrinos. So let's start from the top, that is the crust. The crust is like the solid, and volume is very small, 2%, and mass is 0.5%. But it has the very large amount of the heat producing element, that is the 40%. And this structure is measured by the seismic wave, by the chemical composition and also the boundary of the structures. And here is the mantle that is from the 40 kilometers to the 2,900 kilometers. So this mantle have the very large volume and the mass, and it showed the very large amount of the heat producing element, that is the 60%. So as I mentioned here, we still don't know the mantle is homogeneous or inhomogeneous. And also we don't know details about the chemical composition of this large volume area. And the center of the Earth is the outer core and inner core. The outer core is a fluid and the inner core is solid. So volume and mass is like this. And I'd like to mention that the heat producing element, it doesn't have anything. It's like negligible. But the unknown thing in the core is that we know that density is slightly lighter than the Fe, that could be 10%, but we don't know why it's the lighter and how much, and also what kind of the element cause this light, the density. So this is the structure and the situation. And this slide show you what is the geoneutrinos. So the geoneutrino is the electron anti-neutrinos from the natural radioactive decays. So in the Earth, like that, there's the radioactive element like uranium, thorium, potassium, and it has the beta decay like that. And you can see here it has the anti-neutrino in these processes. And these anti-neutrino called the geoneutrinos. And flux is like the 4.1 times 10 to 6 per square centimeter in second. It's very large flux we have. And here is the energy spectrum of the uranium green, the thorium yellow, and the potassium blue here. And we use the inverse beta decay to detect the anti-neutrino. And the area is the energy region which we can measure using the inverse beta decay. So it has the energy threshold here. So that means that we can only measure the geoneutrinos from the uranium, the thorium, because it's above the energy threshold. So as you can see that unfortunately we cannot measure the potassium geoneutrino in this inverse beta decay reaction. So we need another technology to measure the potassium geoneutrino. So the takeaway message from this slide is that you can see that the number of the geoneutrino here is correspond to the amount of the uranium thorium inside the Earth, and it's equal to the how much radiogenic heat in the Earth. So I'd like to mention a little bit about what kind of energy region we are seeing when we measure the geoneutrinos. So here, this is the very famous figure, the neutrino energy versus the flux. So you can see the geoneutrino located here. So it's like a few MeV region we are measuring. So it's very totally different with like ice cube experiment more than TeV, and even if the water Cherenkov detector is the above the geoneutrino energy region. So the only detector we can measure the geoneutrino is the like KamLAND type Lichtenstein detector. Okay, so I would like to mention a little bit about the history of the geoneutrino. So as we know that in 1956, the Linus and Cohen reported the first electron anti-neutrino detection using the reactor neutrino. And actually, between the Cohen and the Linus, he mentioned about the geoneutrino in their letter. So the almost said that in his letter that it just occurred to me that your background may just be coming from high energy beta decay numbers of the uranium and thorium families in the crust of the Earth. So in this the generation, they just started to measure the anti-neutrino, but they already thought about the anti-neutrinos from the Earth. And also we have the very fundamental foundings by the 1984 anti-neutrino astronomy and geophysics. So that is kind of start of the discussion that we can use the neutrinos to know the Earth. So after like 20 years, the KamLAND made the first geoneutrino measurement in 2005, and then after following that, in 2010, the Italy experiment Borexino measured the geoneutrino. So in the like early 2000, the neutrino started to be used as a tool to understand the Earth. So let me start the Earth's heat balance. So here, this is the measurement and also the modeling of the surface heat flux in the geoscience community. They can actually put many detectors to measure the heat flow in this or entire the Earth surface. And they calculate the heat flux and measuring and calculate the cross heat flux. So we have the number of the surface heat flux is like 46 plus minus 3 terawatt. And this is the example of the Earth model which explains that what kind of energy can contribute to this surface heat flow. So this almost the half comes from the radiogenic heat in the crust and the mantle, and the remaining half maybe comes from the primordial heat, that is mantle cooling in the core. So when we see the mantle, primordial heat, that corresponds to the release of the gravitational energy through the accretion or metallic core separation, or the latent heat from the growth of the inner core, that is the primordial heat. So we still don't know that how much radiogenic heat contribute to the Earth's heat. So we don't know the balance between the radiogenic heat and the primordial heat. So this slide summarizes what we can learn from the geoneutrino measurement as the point of the view from the geoscientific community. So what I can say is that that is the nature and the amount of the Earth's thermal power the geoneutrino measurement can contribute. So the first one is the abundance of the heat-producing element, uranium, thorium, and the potassium in the Earth. So as I mentioned, these uranium, thorium, and potassium has the anti-neutrinos, and we can translate the information to this the abundance. And the second one is the cruise to the planet formation processes. Oh, I didn't mention about this the red one. So the red showing you that this is the current understanding. So the first our estimation of the silicate Earth is like 9 to 36 terawatt, and it has the band like this. And the second one is that we want to know we want to constrain the chondric acid models using these geoneutrinos. And the third one is the amount of the radiogenic power to drive the mantle convection and the plate tectonics. So as I mentioned, the first few slides, we still don't know what kind of the convection mantle has, and also the amount of the power. So if we can know that the mantle geoneutrinos, that we can estimate the mantle heat, radiogenic heat. That is current understanding is that the 1 to 28 hour. So fourth one is that the mantle compositionally layered or they have large structures. So it's also related to the mantle. So we don't know the layers or not. And the LLSVP is the large low shared velocity province. So it's in the oceanic cluster. The seismic wave measurement already see that the very slow speed region, yeah, it's already observed, but we don't know what kind of things happen in that area. So the geoneutrino can directly define the power to drive the Earth's engine. So that means that we can contribute to this kind of fundamental questions in the geoscientific field. Okay, so let me now move to the experimental result. So the two leak scintillator detector experiments have measured geoneutrino in the past. So the one is the KamLAND and other one is the Borexino in Italy. So about the KamLAND, the detector located in Japan and operates from the 2002, and it has the 1,000 ton of the leak scintillator, and the depth is 2,700 meter water equivalent. And so the important number of the geoneutrino measurement is that the ratio between the reactor and the geoneutrino, because the reactor is also anti-neutrino and it shares the energy region, so we cannot separate between the reactor and geoneutrino. So as you know, many of the Japanese reactors surround the KamLAND detector. So up to 2010, we have like 6.7 in this ratio. But after the earthquake, almost all of the Japanese reactor shut down. So after that, it's 1.4. So it's very clean situation for geoneutrino measurement for the KamLAND. So Borexino in Italy, it has about 300 tons of the leak scintillator and a little bit deeper than KamLAND. And they don't have many reactors around the detector, so the ratio between the reactor and geoneutrino is 0.3. So we can say that it's a very clean detector for the geoneutrino measurement. So let me start with the KamLAND result. So this is a common collaboration. It's about the 50 collaborators from the Japan, US, and Europe. So we have the collaboration meeting in Kyoto, but after that we have the online meetings. And this is slide show you the site in the detector. So KamLAND located here, as you can see, this dot show you the reactors. So that means our detector are surrounded by the reactors. So it's located in here, like the 1,000 meters from the Kamioka mine, and it's shield the cosmic ray, and it has the 1,000 ton of the electron insulator, very pure. And we have the about 2,000 of the photon multiplier, which called the PMTs. And we also have the water Cherenkov, the outer detector to beta the muon. And so the as I mentioned before a little bit, how we detected the anti-neutrinos. So here's the inverse beta decay reaction. So we have the anti-neutrino and attack to the proton in the electron insulator. And the proton has the E plus and the neutron, and E plus has the two gamma rays together with the E minus. And these two gamma ray cause the prompt signal. And after traveling like the 200 microseconds, that's neutron captured by the other proton, and it has the 2.2 MeV gamma ray. So it's called the delayed signal. So we use the delayed coincidence method, which is we use the prompt and the delayed signal, which has the time and the distance relationship. So the method has very powerful power to decrease the background. It's like 10 to minus 6 level. So here's the simulated energy spectrum of the geoneutrino and the reactor neutrino. So as you can see, the geoneutrino located here, it's like 1 to 3 MeV and totally covered by the reactor neutrinos. So like KamLAND, we started to have this experiment to understand the neutrino properly, like the neutrino oscillation and the measurement of the oscillation parameters. And after that, we started to notice that maybe this neutrino can use to understand the source of the neutrinos. So one of them is the neutrinos, and that is it can code like the neutrino application. So this is the neutrino flux in the Kamioka. So I'd like to explain about what kind of area we are measuring using the geoneutrino. So this figure shows you the flux as a function of the distance of the detector. So each color shows you the crust and mantle sediment. So when we focus on the vertical axis, we can see that the contribution from each part. So from the crust, we have like 70% of the total flux comes from the crust. And 27 is the mantle, so core is 0, and sediment is like 3%. So you can see that we actually measuring the crust geoneutrino, and we don't have any good information of the mantle when we measure on the crust. So let's focus on the x-axis. So it shows you the contribution from each area. So about the 50%, it comes from the 500 kilometers. So it's shown in this map. So it's about half of the Japan island. So you can imagine that it's very important to understand the local geology to get some geoscientific information from the geoneutrino measurement result. Okay, so here is the rated data set and the reaction neutrino time variation. So when we start to the measurement in the 2002, and this slide show you the data until the 2018. So you can see that the very dramatic decrease around the March 11 earthquake, and we have the all Japanese reactor of period like that, and after the last preliminary result in 2016, we have the updated result. So the currently we have like the 4,397 days data, and this period was 3, that is after the reactor shutdown, has the like the 1,760 days even. So here is the what we are measuring. That is the energy spectrum. So the what we get from the detector is that the energy distribution like this. It's the black dot, and so the figure show you the each background and geoneutrino contribution as a result of the the fitting of this energy spectrum. So we have this like 4,400 days data, and the candidate is like the 1,167 even. So I didn't mention, but like the 1 kiloton detector, like KamLAND size, we get the geoneutrino like 1 event per month. So it's included in the reactor neutrino. So the anti-neutrino candidate number is like this, but the geoneutrino is the 1 event per month. So the background for the geoneutrino measurement is listed up here. Is that of course the reactor neutrino is a huge background. It's depending on the distance or the operation of the reactors. And the accidental background and the alpha and the background is the actually coming from the detector cleanness. So that is like the radioactive element in the detector can be the background. And this fast neutron and the lithium-6 background, it's caused by the muon. So it depends on the how deep the detector. So we have the like the 966 background. So this energy spectrum show you the only focusing on the low reactor phase. So the comparing with the last slide, you can see the very clear distribution of the geoneutrino, which show in the blue. And the 1,760 days that we have the 110 events. And when we just focusing on this low reactor phase, the ratio between the geoneutrino and background is like 1.3. So geoneutrino is more than background in this data set. So as you can see, we clearly measure the geoneutrino spectrum like that. So that means that we can get a better understanding of the uranium and the thorium each contribution. So I didn't mention, but the uranium contribution show you like this dotted line. It's has the event in this entire energy region. While thorium is only the low energy region like this. So the fitting the data that we get the number of the event of the thorium and the uranium independently. Okay, so let me introduce some of the geoscientific findings from the measurement. So first one is the thorium to uranium mass ratio. So from the geoscientific studies that we know that the thorium is more abundant than the uranium. And that ratio is like 3.9 plus minus 1.0. And we also have the chondric analysis which show you this number. And geoneutrinos can test this uranium-thorium ratio independently, and also the direct measurement of the entire Earth. So here's the result. So this plot shows you the delta chi-square distribution of the thorium to uranium mass ratio, show it like this. And this yellow band show you the geoscientific study that's from the chondrite data, and also the BSE model studies, the bulk silicate earth model. So our best fit is the 5.3 plus 6 minus 3.6. And this still have the very huge uncertainty, but the important thing is that our best fit is consistent with the totally different measurement, that is the chondric data and the BCA model. So this is one of the results. Next one is the radiogenic heat. So I mentioned before that we can test the Earth model using the geo-neutrino. So this is the result. So the figure show you the measurement result show in this gray band like this, and comparing with the models which call the low Q and middle Q and the high Q, and this is the fully radiogenic model. So these models correspond to like the 10 terawatt, 20 terawatt, 30 terawatt in the mantle. So the current our result is that they start to reject the high Q model, which correspond to the whole mantle convection model. So I said that we still don't know what kind of convection model has in the mantle, but they started to reject in the 2 sigma in this the whole layer convection models. So maybe it might be that the 2 layers convection model is close to this result. And the low Q and middle Q, it's different types of the primordial meteorite. So we still cannot separate these 2 models, but it started to, started to talk about the separation between that. So the experiment uncertainty is getting close to the separation vector. Okay, so the Borexino result. So this is the recent result from the Borexino. So this is the geoneutrino measurement, the result, and they show the mantle signal is the 23.7 plus minus 10 events. And they say that the sensitivity study using log likelihood ratio method is like the 99.0% confidence level. They reject the null hypothesis in this level. And this figure show you the comparison between the Earth models. So this is the various kind of the bulk silicate Earth model, and this is their estimation. So you can see their measurement is higher than all of the model. So this figure show the almost same kind of the figure as I show you the KamLAND result. So the middle Q, low Q, middle Q, high Q, and fully radiogenic model. So you can see that their best way result accept the middle Q, high Q, fully radiogenic heat. So it still have the large uncertainty, but they prefer the higher radiogenic heat. So here's the comparison, and show you the history of the KamLAND and Borexino result. So you can see that the experiment result are suddenly getting smaller and smaller like this. And this the shaded area show you the geoscientific study calculating each contributions from the crust and mantle. So the mantle has the different models. So the high, it has H, but it's same as the high Q, middle Q, low Q. So you can see that the geoneutrino measurement can only show you the total radiogenic heat of the mantle and the crust. And in the latest, both experiment result has about 1 sigma tension between the data. But it's very depending on what kind of the local crust model they use. So when we get the mantle contribution, we are using the model to estimate how much contribution we have in the crust. So when we talk about the mantle from the current data, it's really depending on the crust model. So we geoscientific community already started to study about the local crust model in the KamLAND and Borexino. Okay, so let me move to the future prospects. So this slide shows you the situation of the anti-neutrino detectors in the world. So this map shows you that the uranium, thorium, geo-neutrino flux. So you can see that in the crust area has the more geo-neutrino than the ocean area. So currently the KamLAND is the only one detector taking that data because the Borexino might shut down by the end of the last year. And Snowplus is filling the exchange data and start to taking the data. So it's the exciting situation. And in China, they have the two very nice detectors. The one of the Juno, which has the 20 times larger than KamLAND, very huge statistics. And the Jinping experiment is very deep, so that means that they don't have any muon-related background. And so I will mention about the ocean bottom detector radar, but the very unique thing is that we can directly measure the mantle contribution in the ocean. Okay, so from this slide, I a little bit show you the situation of the other expecting the detectors. So this is Snowplus. So this slide show you the expected anti-neutrino spectrum together with the reactor and the geoneutrino. And so the good thing about this measurement is that that is the first measurement in the North America, and this is the third point we can get the geoneutrino result. So it can be the multiple measurement. And Juno, as I mentioned, it's a very huge detector, and it aims to measure the reaction neutrino. So it has very huge amount of the reaction neutrino. But together with their very good energy resolution, they fit the energy spectrum, like subtract the reactor spectrum and get the geoneutrino result. So the because of this huge statistics, they can reach to the like 14% uncertainty by 1 year. So currently the common uncertainty is like the 60% in this 20 years. So it's very large detection. And Jinping, so as I mentioned, they don't have so many reactors around them, and it's very deep, so that they don't have any background from the muon related the background. So that they can measure very clear distribution of the geoneutrino. So it's very good to measure in this clean situation. And here I summarize what is the current and the future situation in this neutrino geoscience field. So the upper figure shows what we need, and the bottom is what we run. So the currently we measuring the total radiogenic heat and the thorium to uranium ratio, and started to measure the mantle signal, but it's depending on the crust model. So we have improved the accuracy of measurement and the modeling, and we achieved like that. And in the future, we want to resolve the vertical and the horizontal flux difference. So that means that even if we cross to the reactor and in the cluster, we can separate the crust and the mantle contribution, and they also distinguish the reactor background. So to do this, the separation, that we need a directional sensitive detector. And I mentioned the first the couple of this, right? We need a new type detector to measure the potassium geoneutrino. So let me mention a little bit about the directionality. So to measure the directional information, we need a kind of special Richtschinch-radar that is the lithium Rory Richtschinch-radar. So lithium-6 has the very large cross-section of the neutron, so it can capture the neutron quickly after it happened from the proton, like 20 microseconds. So this neutron has the directional information of the anti-neutrino. It's discussed in this very famous paper. And this figure shows the relationship between the theta n, this is this angle, and the kinetic energy in each energy region. So like geoneutrino less than the 3 MeV, it has the less than 35 degrees. So the neutron, if we can capture quickly, we can know that the direction of the anti-neutrino. So this special lithium Rory Richtschinch-radar already completed the development, and we need a very high vertex resolution detector to separate this prompt and the delayed vertexes. So this is ongoing study, and so this figure show you the angular distribution of the crust and the mantle contribution. So if we can know that the direction, that we can separate the crust and the mantle. Okay, so ocean bottom detector I'd like to mention in the end of my talk. So what we can do with the ocean bottom detector is that identify how much the radiogenic heat in the mantle. So as I mentioned, the current observation is total contribution from the crust and the mantle. So it can describe like the y equal x plus b like this. And in the near future, we have the KamLAND and Borexino snowblast. We can do the multi-site measurement, but we still don't know the, it needs some data very close to the here. That is the direct measurement of the mantle. And here is the ocean bottom detector motivation. So first of all, that is the direct measurement of the mantle, because we have like 70% contribution from the mantle if we go to the mantle, the ocean, because the oceanic crust is very thin and the very low level of the uranium thorium. So we can measure the mantle contributions. And we can also measure the several points, like going to this ocean area like this. So we can get the better understanding of what is happening in the mantle. And this kind of the large and clean detector can be used for the multidisciplinary motivations. So like physics, geoscience, mantle drilling, biology, new technologies, many kind of the multidisciplinary scientific field can be contributed. So for the physics, it can be used like multi-spatial measurement from the reactor neutrinos to understand the reactor oscillation and CP violation. And of course, it can be used for the astroparticle physics. And this is kind of unique situation. It's that the comparing in the mountain, we will have the less neutron background in the ocean. So the neutron background is very serious for the dark matter measurements. So it will be the very good situation for the experiment. Okay, so this is the ocean bottom detector, the present and future. So the idea itself starts from the University of Hawaii in the 2005 when they did the detector design and some development. But nothing happened in this 15 years. But the last 2019, in Japan, the Tohoku University and the JAMSTEC, that is the Japan Agency of the Marine Science and Technology, started to have the collaboration research to realization of the ocean bottom detector. And in this last year to these 3 years, some amount of the budget was funded to make the 20 kilograms detector. So we cannot do anything to like measuring the geoneutrino in this small detector, but it will be the technique test and also the important things is the world first measurement in the ocean with the Lichtensteiner detector. So the JAMSTEC already has the 1 kilometer depth seafloor measurement observatory. So we will deploy this kind of the small detector and taking data 7 months. So now we are doing the several kinds of the development like low impurity PMT shields and Lichtensteiner optimization for the seafloor environment because it has high pressure and low temperature. And DAQ system power supply, that is the kind of problem to be separated from the sea coast. And we are trying to do the deployment, recovery, maintenance, deploy procedure. And the next target will be 1.1 to 10 kiloton to do the technique demonstration and environment measurement the sea. So the 1.5 kiloton detector will be the first clear mantle signal in the ocean. So this is the student simulation result. of the various kind of backgrounds and geoneutrinos. So we get like the like 3 sigma sensitivity for mantle geoneutrino in the 3-year measurement. So in the future, we want to have like 10 to 50 kiloton detector to do many kinds of the science together with the multidisciplinary scientific fields. Okay, so I'd like to summarize my talk. So geoneutrinos are the very unique and new tool to measure the inside of the Earth, which couldn't touch directly from the geoscientific studies. So we can say that the geoneutrino is the only way to measure the amount of radiogenic element in the Earth. So it's very useful to solve the very fundamental mysteries in the Earth. So we have the KamLAND and Borexino measurement result, and it has the geoscientific result like total radiogenic heat, uranium, thorium mass, and test of the Earth models, mantle contributions. So the future of this neutrino geoscience field is that the next target will be the further understanding of the mantle contribution. So to do that, we need the better understanding of the class model to estimate the class contribution. And multi-site measurement will be helpful to do the combined analysis. And I mentioned about ocean bottom detector. It has very strong power to measure the mantle directly, and it will be the breakthrough experiment for the mantle contribution measurement. And it's also the kind of detector can provide a better understanding of the class contribution because if we can identify the mantle, so remaining in the crust, so it can have the multi opportunities. Okay, so that's it. Thank you very much.
Okay, well, thank you very much. So I'll open it up for questions. If people want to type them in the Q&A or raise their hand, they're welcome to do so. Maybe I'll start things off. I had one question. Can you say a little bit about the sort of immediate future prospects? So is currently the estimates of the crust heating and the thorium to uranium ratios are sort of factor of 2 uncertainty, so they're consistent with the expectations, but not strongly constraining them. So there's presumably ongoing data from KamLAND and data that will, in a few years, that will start coming from SNO+, and you mentioned Juno maybe being able to get 14% in a year. Can you sort of give an idea of, on what time scale might one have measurements that are several times better than the current ones from any or all of those 3?
Yes, so I think the very near future, like the several years, we can get better understanding of the local crust together with the geoscientific community. So that means that we can get the better understandings of the mantle contribution, even if this current data set. And and together with the SNO+, if we use the same kind of the crust estimation, we can do the like combined analysis. So together with the KamLAND, Borexino, SNO+, it's also we can get the better understandings of the mantle contributions.
Okay, so it looks like we have a question from Dave Stevenson. You want to go ahead and ask Dave?
Yes, you didn't emphasize it, but you seemed to be suggesting that these kinds of measurements tell us something about the form of the convection. For example, you mentioned whole mantle versus layered. I would have thought that's impossible, even with better data. But maybe you are appealing to particular models that you're not responsible for. Anyway, I'm curious as to what you think about that.
Yes. So yeah. So the categorized as the high Q, middle Q, low Q. It's the roughly separated as the whole layer and the several layers. But as you said, there are many models, and it cannot be categorized like three. And also as you can see, the experiment uncertainty still can cover the models. So it's difficult, but it's getting close to say something.
But okay, I'm going to question that, because it would seem to me that it doesn't matter whether it's high, low, or middle Q. In all cases, I could have whole mantle convection. After all, I can have whole mantle convection with zero radiogenic.
Yes.
You can't make it entirely radiogenic because it's a question of heat from the core. But I can have whole or layered for all choices of your result. That's my claim. But
okay.
Are you saying that you think otherwise? Maybe because of, I mean, of course, there are lots of models out there, and it's true that particular models lead to particular outcomes. I know about some of these models, but knowing about the models, I'm suspicious of them.
I see. Yes, yes. All you said is I agree with everything. So yes, what we are doing is that putting the additional information, so it can be together with the geoscience community and also the astronomical communities, I think.
The ocean bottom approach
yes.
in future prospects would seem to me to be the best way to learn more about structure, because then you can clearly separate. I mean, you talked about crust and mantle, but of course, we know something about the ocean crust. We know it's rather small contribution, and so
yes.
it's a cleaner separation. Crust, of course, is spatially variable, and so you have the spatial variable that makes it complicated. So you have to hope that the ocean bottom approach will actually be carried out. That would rather than doing measurements on the continent.
Yes, right. yes.
See, so we have a question. Oh, sorry, go ahead and finish.
It's okay. Yes, let's go ahead.
So there's a question from Wanchun who says, how is the energy of the neutrinos determined, and what are the accuracy of the measured energies?
I see. So the current I think it's talking about energy resolution. It's like the 6% or something. So it shows you the energy spectrum result like this. I mean, yes. So if we can get the better energy resolution, that means that we can get the better separation between the uranium and the thorium. Is that answering the question?
Yeah, so there's also a question from Alan Weinstein, which says it was an old idea from Lederman to build a floating accelerator and a floating detector on opposite sides of the Earth and try to do neutrino tomography, I guess, with maybe the external neutrinos. Is that still being considered, or is that hopeless?
I see. So that kind of things, we need very huge detector. It's like much times of the ice cube. And I think if we do the tomography, the kind of detector needs several places. So it's yeah, theoretically it's useful, but the reality it's difficult to make that kind of detector. But it still have the discussions.
Let's see. So there's a question from Michael Gurnis. Do you want to ask your question?
Sure. Thanks. I just wanted to follow up on Dave's questions and comments. And I agree that the way to distinguish between these models is to have this spatial aspect to it. So here's a specific question about the ocean bottom one. So will it be possible, let's say with a 20-ton one, putting that on the seafloor, will you be able to detect direction where the neutrinos are coming from that experiment? And how long will you need to keep it on the ocean floor? And then third, do you need a ship tethered to it, or can the ship drop it down on the seafloor and come back after the period of time, which was the second question. So I guess, thanks.
Okay, thank you. So the first one, the direction, so currently the kind of KamLAND type detector, we cannot measure the directionality because we lose the directional information because of the neutron traveling. So even if we have like the 1,000 statistics like KamLAND, that we cannot identify the direction. So that is the kind of the unfortunate situation in this the Lexington radar. But a little bit mentioned about the lithium lowly Lexington radar. So if we have the lithium lowly Lexington radar, like the like large, like 1.5 or 10 kiloton, it can be done with the directional information. But we need the studies to realization of that kind of new technology. And so how long? Yes.
Yeah. How long?
Okay. How long? So the simulation result, we use the 1.5 kiloton detector, and it's like maybe it's should be here. So like 3 years measurement, the mantle distribution is like 30% asymptotic. That is the current measurement estimation. Yes.
Sorry, I didn't understand that. 3 years?
3 years. Yes.
3
for
years.
the 30% uncertainties with the 1.5 kiloton.
Right. Okay.
I guess if one got up to 20 tons, you could then do many sites in a few years. Is that?
Yes, if it's like 10 times bigger than this, it can be reduced, that the measurement time.
I guess Michael's other question was whether the ship has to stay above the detector.
Yes.
Or whether...
Yes, so the ship, like the mantle drilling, it can produce the electricity. So taking the data, we need electric power, and having the kind of ship, it's very helpful, but it's also very expensive. So maybe it's better to be separated and just deploy and like getting the electricity from the seafloor cable. That is one kind of the design of the detector. But when we talked with the Jamstick people, that is, which they already have the very huge ship. So when they do like mantle drilling, they stay like 1 year or something. And so together with the purpose that we can get electricity and we can do the mantle drilling together with the geoneutrino measurements. So it can be another possibility.
Thank you very much.
So on the question maybe related to power, that I guess particularly in the Northwest Pacific and around Hawaii, there are a lot of reactors moving around. And some of them, like the aircraft carriers, are visible, but some of the undersea ones, probably nobody wants to talk about where they are or when they are. Are those a source of confusing background potentially?
So that kind of things that I think it's kind of negligible. I think it's very small power, and also depending on the distance, but it doesn't affect to the measurement, I think.
Okay, because I thought the aircraft carriers are sort of gigawatts right now, though I guess it depends on how fast they're going, how much power they're using. But... Okay, well, we'll declare the official part of the colloquium over. If there are people who want to stay along for sort of informal conversation, I guess Hiroko is available for another 20 minutes or so. So I hope a few people will stay around to chat. But otherwise, let's thank her for a wonderful talk. And
thank you very much.